Hello, my name is Arno Rauschenbeutel. I'm an experimental physicist working at the Humboldt University in Berlin. Two months before the Berlin Wall fell, I was on my school-leaving trip to Prague. At that time, the German embassy was resort to numerous Eastern German refugees. I remember the streets full of abandoned Trabant cars, and I remember a square with a central statue, and the German refugees tied their car keys to the wrist of that statue. That was a strong statement. It was a statement of both hope and despair. It made me feel involved emotionally. Seeing the refugees cheering to Genscher in the garden of the embassy, seeing the Berlin Wall fall soon after, my trip to Prague gave another dimension to me for this historical event. For as long as I can think, I wanted to become a scientist in fundamental research. So what I'm doing now is definitely a dream come true. It is wonderful to understand something for the very first time. And it is very satisfying to see your own ideas realized. In my research group, we catch single atoms with glass fibers which are 100 times thinner than a human hair. We tame quantum particles, so to speak, by putting them on a leash. In doing so, we contributed to breaking the wall of quantum nanophotonics. There, one seeks to couple atoms or molecules to light in tiny structures. The aim is to realize components for next generation communication and information technologies. What is the challenge that your project addresses, and what is your solution? Quantum mechanics enables us to communicate in a fundamentally tap-proof way if we encode the information in single photons. Of course, for this, we need sources that are capable of emitting single light quanta. Atoms are, of course, a good choice here. Ideally, these atoms would then be coupled to optical fibers so that the emitted photons can be directly sent to the receiver. This is where my research comes in. We are working on establishing an efficient interface between atoms and fiber-guided light. For this, we heat an optical fiber and pull it like a chewing gum. Eventually, the fiber is 100 times thinner than a human hair, and the light slightly protrudes to the side of the fiber. We then take tweezers out of laser light and hold atoms near the fiber where they efficiently couple to the light protruding from the fiber. While experimenting with our nanofiber-based atom-light interface, we came across a strange phenomenon. The atoms only interacted with light that was traveling forwards through the nanofiber. Light that was traveling in the opposite direction was completely ignored by the atoms. That was very surprising because the atoms are much smaller than the wavelength of the light. They thus should not be able to know from which direction the light is coming. A direction-dependent atom-light interaction, nobody was expecting this at this point. And it quickly turned into a completely new research direction. It also allowed us to realize one-way streets, roundabouts, and even turnstiles for photons, some of which we could patent. So on our way to quantum communication, we came across an unexpected research result which turned out to be a game changer in many areas of quantum optics. Today, optical fibers are the backbone of the modern information society. Security of communication is an important aspect, naturally. So this type of work on quantum communication has an immediate societal benefit. Handling and processing complex quantum states of atoms and light sometimes feels like juggling 10 plates at the same time. It is thus quite challenging to make the transition from laboratory experiments to real-life applications. So whenever my mind is free, I tend to think about how we can make our systems easier and more manageable in order to make that transition. My 7-year-old daughter is fascinated by the fact that her dad works with atoms, because everything is made of them, although you cannot see them. She also loves her laser pointer, and she likes to ask me questions about these things, which are sometimes not so easy to answer.